Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video in differential calculus, we're going to go ahead and use our calculus techniques to help us graph functions, specifically the cube root of x squared minus 9. Now, you should have already gone through some instruction on how to start graphing functions using calculus. And so I'm just going to write down in the order that I would tackle a problem like this. The very first thing I do, even before I start graphing, is I list out the domain of the function. So the domain of this function, because it's a cube root, you can plug anything you want into the cube root. So the domain of this function is all real numbers, negative infinity to positive infinity. I start with that just because once I know that there's a domain issue, if there is one, then it reduces the amount of work that I have to do. It also informs me as to possible vertical asymptotes. Anyhow, after I take care of the domain, I do the intercepts, or I find the intercepts. And notice that both of these topics are actually old school algebra topics. So I'm actually starting my graph of a function using calculus with the earliest material and working my way up to the most recent material. And so the intercepts for this function, well, I know that when I input 0 to the function, I get the cubed root of a negative 9. And you could simplify this if you want to, but I'm just going to write that as a negative cube root of 9. I don't know what the cube root of 9 is offhand, but I can at least write that. So that is the y-intercept. And now I'm going to go ahead and find the x-intercept. Let me write this in, cube root of 9. And the x-intercept occurs when the output is 0. Obviously, you should know this. I'm just going through the algebra, right? And this equation is true as long as x is either 3 or negative 3. So the x-intercepts, notice I'm not really doing the algebra here, because we already know how to do algebra, so I just didn't bother solving that out. I know it's plus or minus 3. All right, next thing I'm going to do, again, going through my algebra and working with this function here, I'm going to look for symmetry. So symmetry is always a tricky thing because a lot of people forget to look for it. In this case, it's actually advantageous. So symmetry, there's 3 different kinds of symmetry. You have an odd function, an even function, and then you have something called translational symmetries. But translational symmetries, you're generally looking at trigonometric functions like sine or cosine, and this is neither of those. It's not necessary for it to be a trig function. There are some non-trig functions that have translational symmetry. However, they're few and far between. So in this case, I'm going to look for odd or even. And to test a function for odd or even, you evaluate the function at a negative x. And so if we do this, we have the cube root of a negative x being squared minus 9. And so that ends up being the same function that we started with. So that is just f of x. So now that I know f of negative x is f of x, I know that this is an even function. Now, what can happen as you're working through this process is you could kind of lose all the information because you're going to be doing a lot of writing. So I'm going to highlight kind of my results so that I can keep track of them. I often, when I do these problems, forget my symmetries and end up graphing the whole stupid thing. I would prefer not to do that. Now I'm looking for asymptotes. Again, growing through calculus or through the math series here. So usually you do symmetry in maybe a college algebra course, and you also look at asymptotic behavior in a college algebra course. So we're just going to go ahead and take a look at asymptotes. Vertical asymptotes, well, there are no domain issues, so there's no vertical asymptotes here. All right. So I don't even bother looking at that. And then horizontal asymptotes, well, if I'm going to look for horizontal asymptotes, though, that would be behavior as x is going to positive or negative infinity. And you could see very quickly as x goes to, let's say, positive infinity, that this function will just head off to infinity. So there's really not a horizontal asymptote. Obviously, to have a horizontal asymptote, this limit must be finite. And the same is true if you had your limit go to negative infinity. Okay, so in both cases, the limit is infinite. It's not finite, so therefore there's not a horizontal asymptote. Now, there's one other asymptote that you could possibly check for, and that would be an oblique or a slant asymptote. I usually call them oblique asymptotes. These are asymptotic behaviors as time goes on. And actually, just to kind of give you a heads up as to what an oblique might look like, I'm just going to slide this over. An oblique, I'm going to use the function y. Y equals, let's say, 2x plus 1 plus 3 over x minus 2 or something like that. An oblique asymptote for this function would be 2x minus 1. And the reason why is because as x goes to infinity, this last term is just going to tend to 0. So as a recall that a function g of x is an oblique asymptote for f of x if the limit as x goes to infinity of the difference of those two functions tends to 0. And so in this case, I would say, well, x plus 1 is an oblique asymptote for this function, even though the function is not equal to x plus 1. I would say that is the oblique asymptote because the limit as x goes to infinity of the function itself, which is 2x plus 1 plus 3 over x minus 2, minus what I'm claiming to be the oblique asymptote. That limit as x goes to infinity. Well, you can see the 2x's cancel, the 1's cancel, and that's going to be the limit as x goes to infinity of 3 over x minus 2, which is 0. So therefore, by definition, this function 2x plus 1, let me highlight it, is actually the oblique asymptote. Most people would call that a slant, but the reality is that as you, there are a lot more oblique asymptotes than there are slant asymptotes, so I just call them all obliques. Anyhow, that's by definition. So generally speaking, you can kind of eyeball really quickly whether a function, a given function like our function here, has an oblique asymptote if there's a piece of this that tends to 0 as x either goes to positive infinity or to negative infinity. But there's not a piece of this that will turn to 0. Usually when you're looking for oblique asymptotes, you're looking for a 1 over something with x's here, or you might be looking for 2 to the negative x, right? Something that tends to 0 as x goes to infinity. So you're looking for expressions of that form, and those don't exist in this function. So I'm just going to quickly say there's no oblique asymptotes either. So there's no asymptotes at all within this function. Now, the next thing I need to do, let's see, we've gone through domain, intercepts, symmetry, and asymptotes, all algebra topics. And now we're going to graduate into calculus. So calculus, we're going to worry about the stuff concerned with f prime. So what is f prime going to tell us? The first derivative of a function tells us when the function's increasing, when the function's decreasing, and therefore when the function might have local maximums and local minimums. So everything about the first derivative is what we're going to worry about here. So let's go ahead and focus on the first derivative of this function. Again, I have to take a look at the function. It's the cube root of x squared minus 9. So let me write that just above here. F is equal to cube root. In fact, I'm going to write it this way. F is equal to the quantity x squared minus 9 to the 1/3 power. Okay, let's go ahead and take its derivative. That's 1/3 x squared minus 9. and then subtract 1 from that exponent, so negative 2/3. And by the chain rule, hop inside and take the derivative of x squared minus 9, which is a 2x. And you should probably clean this up. If you do not, it will be pretty terrible. I'm going to go ahead and factor a 2/3 out of this whole expression, and I get x over, let's see, the 2/3 power of x squared minus 9. And the reason why I kind of clean it up is so that I can see the domain issues with this. And so I make a number line here, just like you would for sign charts for rational functions, rational equations, way back in your algebra course. And since I know this is an even function, and that's usually the thing I forget, but this is an even function, so I know that there's symmetry about the y-axis. So what I'm going to do is only concentrate on everything from 0 and to the right. So starting at 0, and I know the behavior will be symmetric on the other side when I go to graph it, okay? So let's see, starting at 0, f prime, so we're looking for critical points. So critical points, or critical numbers, maybe I should say. Critical numbers of f. Well, I can see in f, or f of f prime, well, of f, yeah. So the critical numbers of f, well, that occurs when f prime is 0, so that occurs at x equals 0. And we also have two places where the derivative is undefined, and that would be at plus or minus 3. So I'm going to say x equals plus or minus 3, and that's where it's undefined. Those are kind of important because there's a lot of ways a derivative can be undefined. There's a lot of implications to when a derivative is undefined. Either you have a kink, a cusp, or a corner, or you might have a vertical tangent line there. So what I'm going to do is wherever the derivative is 0, I'm just going to put a little pipe there. And wherever the derivative is undefined, like 3 and negative 3, even though I'm not going to worry about the negative 3 because of symmetry, I'll get that when we graph the other side. I'll put an open circle, kind of like what you would do when you're talking about the domain of a function. I cannot include 3, but I can include 0. And now I'm going to test the first derivative here for signs, S-I-G-N signs, that is. So for example, pick a number between 0 and 3, like 1, and you'll see that f prime is going to have, so maybe I should write this down, at x equals 1, f prime of 1 is actually equal to 2/3 times 1 over negative 8 to the 2/3 power. Now that the 2 in that numerator is a squaring, and so that forces that denominator to be positive, and so this entire statement is actually greater than 0. And so I know that the derivative is positive, which means that the function is increasing. And now I'm going to go ahead and look at a number greater than 3. Often, for me personally, I just choose ridiculous numbers. F prime of huge. Usually in class I'll say like, what's f prime of a billion or something like that. So you get 2/3 times some huge number over, again, some huge number, not the same one, but whatever, to the 2/3 power, but that's still very positive. So I happen to know this function, at least from 0 to infinity, is increasing, and at 3 itself, there's some type of issue with the derivative, which means there's a kink, a cusp, or a corner, or it's some type of vertical tangent line. So let's see, so far, maybe I should highlight that information. So far, I've got this highlighted information working for me. Okay. Usually when you find these critical points or critical numbers, you would go ahead and at the same time find out the value of the function at those points. So normally I would say, okay, well, I know 0 is a critical point. Let me see what f of 0 is. But we've actually done that already. F of 0 is this guy right here. and it is 0, negative cube root of 9. And we also have found the function value at 3. The function value at 3 is 0. So what I'm going to do, just as a reminder to myself, is I'm going to say this point is 0, negative cube root of 9. And this point right here is 3, 0 when I go to graph it. You don't need to write that there, but it's kind of a nice thing to have. Okay, so now we have increasing. We could see the increasing, decreasing behavior. And we can also see that there's really not as far as on the right-hand side of 0, there's not a local maximum nor a local minimum. Finally, step 6, so we go into the second derivative. Now, the second derivative is going to tell us everything about concavity, concave up, concave down, and possibly inflection points. So, of course, we need to find out what the second derivative is. F double prime of x is equal to, well, that's the derivative of f prime, which is this 2/3 of ugliness here. And so I'm going to go ahead and use the quotient rule. 2/3. Derivative of that numerator is a 1 times the denominator, which is going to be the x squared minus 9 to the 2/3 power, minus the numerator, which is x, times the derivative of the denominator, which is 2/3, times x squared minus 9 to the negative 1/3 power. And remember, multiply by the chain via the chain rule, multiply by 2x. And that's all over that denominator squared. The denominator here is x squared minus 9. And we're just going to square that to where it's a 4/3 power instead of a 2/3 power. There's quite a bit of cleanup you should be able to do here from your prerequisite pre-calculus course. So I'll go ahead and do that. Let's see. First thing I'm going to do is I'm going to multiply both numerator and denominator here. There's a couple, actually. There's a couple actions you can do. One, some people will say I'm going to multiply the numerator and denominator by x squared minus 9 to the negative 1/3 power. That's actually how I would visualize this. And I'll also multiply numerator and denominator by 3. So I have 2/3 multiplying the numerator and denominator by 3. Let me go ahead and at least take care of that. I'll get a 3 downstairs. I'll get a 3 in front of this quantity. And again, I'm multiplying numerator. Let me go ahead and write that in blue, in fact. Multiplying numerator and denominator by 3 times the quantity x squared minus 9 to the 1/3 power. And this is just a prereq skill, so I really shouldn't be talking about it too much, but distribute that in, and I'll get an x squared minus 9 to the 3/3 power, or just x squared minus 9. And let's see, x times 2 is a minus 4x squared. X squared minus 9 to the 1/3 power times x squared minus 9 to the negative 1/3. They cancel out beautifully. And then downstairs, x squared minus 9 to the 5/3. Cleaning this up, I get the following. I'm going to factor that 3 off that denominator, so I get 2/9 times, I have 3x squared minus 4x squared, so it's a negative x squared, and then minus 27 all over the x squared minus 9 to the 5/3. And you know what, I might as well just factor the negative off that numerator, so negative 2/9 times the quantity x squared plus 27 all over the quantity x squared minus 9 to the 5/3 power. Okay, I feel pretty good about that. So let's go ahead and create a number line, a sign chart, if you will, for f double prime. It's not technically called, these are not technically called critical points, but I am trying to find out when is the second derivative, f double prime, when is that 0? And when does it not exist? So they're kind of like critical numbers in a way, but they're just not defined to be critical numbers. Now, if you notice, f double prime is going to be 0 when that numerator is 0. Well, that numerator is never 0. So, oh well. And f double prime is not going to exist when that denominator is 0, which is at plus or minus 3. Now remember, recall from our discussion with f prime here, Since we're only doing symmetry, or since we have even symmetry, I'm only worried about the right-hand side. So I'm of 0, that is. So I'm going to go ahead. I'll mark 0, even though 0 is not technically a critical point here or it's not where the second derivative is 0, nor is it where the second derivative does not exist. But I'm marking it there nonetheless, because I'm just saying to myself, listen, I'm only concerned about the right-hand side. And I know that at x equals 3, the second derivative is non-existent. And so I'm going to test a point between 0 and 3, and again, beyond 3. So f double prime at, let's say, 1 is going to be a negative 2/9. And then times 28 over negative 8. And this is to the 5/3 power, which means the negativity will still be there. So I'll have a negative 2/9 times a negative number, which means that this is going to be positive, which means I have a function that's concave up there. And now f double prime at any number greater than 3, I'll say huge, is going to equal negative 2/9 times huge over huge to the 5/3 power. But those huge numbers are positive. That's all I care about. So you have a positive times negative, so this is going to be a negative here, which means your function should be concave down after 3. I'll highlight that, highlight that. All right, let's group all this information together. Now, when I do this, I typically, if I'm working on a board, which I commonly am, I will go ahead, whoops, that is the wrong highlighter. So I will go ahead and rewrite my f prime and my f double prime information up above. So you can see that I'm kind of repeating this a little bit. I'll put a 0 here. So this is where 0 occurs. And I know that they both have issues at 3. Okay. And I knew that the function was increasing. Oops, I don't want to do that. I knew the function was increasing and then increasing, and it was concave up and then concave down. Okay, and then those open circles are telling me that those are kind of issues, so I need to use the graph to help me out. I also will note the function values there. So at 0, I know it's negative cube root of 9. And at 3, I know the output is 0. And I'm going to use the fact that it's an even function. Now I'll try to, I know I'm sort of, in a way, cheating because I have a very nice graphing utility here. But I'm going to try to align these here. So this is supposed to be 3 right there. I'm not going to write it in because of the fact that I'm going to be drawing through it. So let's see. At times 0, the output is a negative cube root of 9. Well, that's slightly larger than a negative 2. Okay. When I say slightly larger, I mean in magnitude. So it's probably a negative 2.1 or something like that. So because I don't have a calculator, I'm not going to give you an approximation of that. I'll leave it as a 0, negative cube root of 9. I'm saying it's close to negative 2 because cube root of 8 is 2. So that's close. Now I know it's going to be increasing from this moment that I draw this point, and it's concave up. So when I draw, I just start hashing out kind of what I think it's going to look like. That's concave up and increasing. However, I know that at 3, there's going to be some type of issue. It's going to pass through 3, 0 because it's defined there. But momentarily, the function will go vertical. How do I know it's not a kink? It's because the function, to get a kink, it's got to go increasing to decreasing. I mean, it doesn't necessarily actually have to go increasing to decreasing, but it's likely to go from increasing to decreasing. So we have this concave up and increasing. And then after 3, it's still increasing, but now it's concave down. Something like this. It looks to be increasing and concave down there. There we go. And so what you can do is copy this to the other side. and use the symmetry. So all I did was rotate this around the y-axis there. And you have your entire graph. Now, it would be nice to actually plot those points, right? So 3, 0 now, and 0, comma, negative cube root of 9. Seems like a lot of work for a simple graph, but this is a fairly accurate graph. And in fact, I probably should showcase this graph. And I'm just graphing this, or I just graphed this via Desmos, and you can see that is really, really close to what I have here. So that is an example of using calculus to graph. And in the next video, I'll show you how to graph if you do have some type of oblique asymptote.